The world as we know it today of traditional telephony technology. Now, this is going to be a walk through the existing infrastructures that run our phone networks of today. The reason why we need this is because we need to interface with these systems for many years to come. This is essentially the foundation of the telephone network, and it's not going anywhere fast. So, in order to bring up our new IP telephony systems, we're going to need to integrate those systems with the world of traditional telephony. So we'll start things off by looking at the parts of traditional technology and what they do. Now, just so you know, if you haven't seen this before, this stands for time domain multiplexing. It's kind of a loose term that we use to describe most of the existing systems in offices today. It's a way of communicating across a T1 line or E1 line to the PSTN. Now, of course, it's not directly accurate to call all traditional telephony systems TDM. However, it's kind of like when you talk about existing networks and you talk about how data travels across the data network, we always say, oh, yeah, the packets are going across. Now, that's not technically accurate. You're really supposed to be saying the bits or even frames are going across, but we kind of use packets as that generic term. Well, that's kind of how I describe the old world is the TDM. And I've got to stop saying that. I keep saying the old world. And it's not the old world. It's been around for many years, but it will be here for many years to come. We'll also look at the infamous central office in the CO and take kind of a little tour through what that looks like. I've actually had the opportunity to go through many COs and see from the very low end up to the very high end. So I'll tell you what those are all about. PBX versus key systems. What are the differences? What are the key strengths of each? And I also want to look at what protocols, and I kind of put my little quote unquote protocols are used in TDM because they're not technically protocols as our data minds understand them, but these are the signaling methods that they use. Finally, we'll look at multiplexing voice, how we send multiple voice streams across a single line, and the technologies used to make it happen. As I've taught IP telephony classes, I've really found that there's two schools of people that are going through them. One is the standard data person, the network engineer that is learning the new IP telephony technology. The other is the PBX person that is looking to add to their skills of telephony by moving into the IP telephony world. Now, I found that the learning curve is a lot steeper for somebody coming from the PBX world into the traditional world because they have to learn all the networking foundations of IP and learning subnetting and IP addressing and so on, in addition to everything that they know about the PBX world. It's actually much lower for a data person learning this technology because all we really need to know, and I say we because I'm one of those person that's learning the old world, is the connections and signaling types of interfacing with the PBX person. Now, we don't really need to learn the inner workings of a PBX system, as in how to program it and so on, because that's still a specialized skill set. Just about every PBX vendor has their own proprietary system of how to manage that. And that's why PBX engineers have a specific skill set, as in they know how to work with a Lucent PBX or a Nortel. It's very focused because each one is like relearning the technology from the ground up with a very few similarities between them. So in this world, this is a 10,000-foot view of those connection types. Again, focusing on the signaling methods between the PBX and the CO, because that's really what we're going to look at. Let's start off with the central office right here at the core. In the CO, we have our telco switches, and these are, enormous offices ranging from the neighborhood size of, maybe a 16 or 1700 square foot building up to the major metropolitan areas where we can have an entire 3-floor or 4-floor building dedicated to that area. Now, these telco switches can interface directly with local loops, and this is where services are delivered through a loop. And a local loop is essentially an underground wire that's going in a huge loop throughout an area. And that loop dictates what area the telco switch services. Now, I'm not going to draw the whole loop before it gets too messy, but off of this loop, you'll start having your analog devices, maybe your standard telephones that are plugging into houses. And when I have a little phone hanging right off this loop, remember that this is encompassed in a house within itself. You have a little house sitting right here with a flat ceiling. I'm in Arizona where we have these Pueblo houses, right? And the house is really a loop too. You have a loop inside of your house that connects here. And that's why, for instance, I can be in my kitchen talking on the phone, and my wife can be in the back bedroom and pick up the phone, and she's on the same line. It's because we're really sitting on the same loop. So we have all these analog devices tying into this loop. And that's really the first major type of device that exists. Now we can have that loop connected from this telco over to a PBX or even a key system, and that's known as a central office trunk. The PBX system is like having your own central office inside of your company. These phones inside of here, most likely, if they're connected to a PBX, are considered digital phones, which means the signaling method is all digital. It's all ones and zeros. We don't have to really handle that single analog type of connection, which is what our homes use. Now this phone connected to the PBX will be assigned its own extension. We'll say extension 4000, and down here we have extension 4001. And we have all of the interconnectivity of these phones handled by this local PBX system. If one of these phones ever dial 9 or whatever outside access code the company uses, they'll end up going across the CO trunk, and this will be the connection off to the central office. Now, depending on the size of this company, it could very well be that that CO trunk is just maybe a couple analog lines, and that would be for maybe a company that had, say, 10 phones inside of here. They could call each other and maybe hit a couple of them hit 9, get an outside line. Now you could also upgrade that to a digital line, and that's where we start getting our fractional T1s and our full T1, or even if we're in Europe or Japan, you run into the E1/J1 lines that allow you to connect out to the PSTN. And these full T1 lines can handle 24 channels, typically, of voice going out to the CO. And some types of T1 may end up taking 23 channels, but we'll talk about that later. E1 lines are usually around 30 channels, and typically J1 follows that same standard. So we have these trunks that allow us to connect from our inside system out to the central office. Now, sometimes you may have a telco company that, or not, sorry, telco company, a business that has multiple locations. We'll say this location is out here in Arizona, and then this location is maybe out in Florida. And they want to integrate these two buildings together and make the users feel as if they're directly connected. Maybe over here in this building we have extensions 5000 and extension 5001 down below. And I want to be able to just dial over here using a 4-digit extension and not really pay any long distance. Well, at that point, we might buy one of these tie lines. And the tie lines allow us to connect over to these two offices, meaning they believe they're directly connected. The central office is then transparent. And that allows these two companies to dial each other through 4-digit extensions. Now, all is not free in this world. The tie line does have a monthly cost. And depending on how you negotiate that with the service provider, that monthly cost may include things like long distance charges. For instance, if we have just a basic tie line, we may pay a monthly tie line charge plus all the minutes that are used over that tie line. If we're a big enough company and have a large tie line between those locations, the long distance may be wrapped into the monthly charge of that tie line cost. So you can imagine, with handling all these types of connections, the central office has quite a bit to do. Now, I have the wonderful experience of working with a company back in the day that was called US West. They're now called Quest. But I actually had it was about an 8-month contract with them where I trained their technicians on how to install DSL service when DSL had first come out. So I got to travel all around the west coast of the United States, going into all these central offices and provisioning lines and so on. And before I had that opportunity, I just kind of imagined this central office as maybe as many of you do, as this cloud. And it was kind of like the magic cloud. It just makes you connect to services through the telephone company. But after going in many of the real upper end and many of the real low end central offices, I now have a really good idea of what happens in that mystery cloud. This is a picture down here that I had of one of the central offices offices I walked in, this was actually one of the smaller central offices that ran a residential neighborhood. The building was, I would say, about 1,000 square feet, and was, had a small little lot that it was on, a parking space for 2 or 3 people that could work at this. And we walked into many of these different central offices. There's usually one person on staff there that typically, not to give them a bad name or anything, but they had their feet kicked up on the counter and they were just munching a sandwich or something like that. And they were just watching a monitor and doing just standard day-to-day stuff of bringing these connections up. Now, in this central office, this is pretty much the central office that managed the connections for a local loop. For instance, this would be a neighborhood connecting out here of, maybe 1,000 people or 1,500 people or so that were all starting to come off of this local loop. Now, one of the things that, coming straight from that DSL category, one of the things that you had to be sure of is if somebody wanted DSL service and data connections on that central office, they had to be a certain distance from the central office. Like right about here, would be the cutoff point, and these people couldn't get DSL service, and these people could, because you could only get so much bandwidth squeezed through the line before the signal starts to degrade to the point where it can only handle basic voice service. And I'll talk about why this is. I'm telling you this because later on we'll talk about the technology they use to squeeze those frequencies across that line. But this central office managed all these different functions that pretty much drive your phone service of today. I already talked about managing the local loop, which is, connecting to all your houses and providing that phone service inside of each one of those houses. They had the call routing that they would handle. And this is where when you dialed a call, it would come into the central office and they would have essentially the database of databases that connect them to the rest of the central offices all around the world. Each one of these central offices, I mean, this is kind of a zoomed in view, they handle their own local loop. And, if we kind of focal in on this, this is one central office that connects to another central office, which connects to another central office, and goes up and up in chain. And you eventually reach the central offices of the major metropolitan area. And it makes these things look like a little, cookie baking shack or something like that. I've been into the central office of, where was I mesmerized and taught a hard lesson. It was in Minneapolis, St. Paul, Minneapolis, central office. And I walked into that thing after being in these. This was the first major one that I had walked in. And it was like, in here they had the concrete floors, dust and dirt and, brooms and sweeping. I walked into the central office of St. Paul, and it was just like, whoa, gleaming of the lights off the shiny spit shine floor. And we didn't have these kind of switches. They had huge switches with lights and gizmos, and you just had the fans, and oh, it was cool. And so I walked in there, and of course, me being me, the goofball that I am, I walked in with the technician I was working with at the time. He goes, "Yep, welcome to the Minneapolis St. Paul central office." And I walked in, I go, "Wow, so if I wanted to put a bomb somewhere, this is where I'd do it, right?" And it was kind of like one of those movie moments where all the phones stop ringing and all you can hear is like whoosh. And then, I was kind of like, I wasn't supposed to say that, was I? And he kind of had that solemn look of, no, 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 you don't talk about that kind of thing here. Because this thing literally controlled the phone service for all major areas in the Minneapolis-St. Paul area. And it's really neat if you start getting into the inner structure of all these COs. It kind of works like the IP addressing, if you will, of our data world. Kind of like where we had, a small subnet of, we'll say 192.168.1 down here for the neighborhood. And then you move up and you kind of summarize, and maybe you have a 192.168, at this next major stop, and we have a summary mask of like, 0.0 / 22 subnet, where you kind of summarize a range of 64 addresses or so. And then you come up here to this major area, and you have 192.168.0.0 / 16. And it's kind of like our hierarchical IP addressing, but now it's in terms of area codes. And maybe this is the service for the major area codes of 802 or 920, and they come up here to the the more higher central office that summarize the area codes. And as you break it down, you get the area codes for a neighborhood, or maybe just a prefix of that neighborhood, where you have just the 802, 777 numbers at that central office. So that's kind of how the central office works with the call routing structure, is they route within these different area codes. You also have a battery running these central offices. And this is something that we need to get used to in the IP telephony world, is when the power goes out, the phones stay on. Now, I know this has changed in recent times because just about everybody and their brother has these cordless phones that plug into a wall. And when the battery goes out, we lose phone service too. Or I should say, when the power goes out, we lose phone service because they're plugged into a wall. But standard analog telephony means that when you have a normal phone, it's powered by the CO. So if the power fails, they have a battery backup there. That means phone service resumes. And when we're looking at our IP telephony, we have to take that into account. People are used to the phones staying online even if the power is out. Now, these COs also have a ring generator, and we'll look at the voltage that they use. But when a phone goes off hook, voltage begins to flow through that phone. They have a ring generator. The voltage that dial tone uses is DC voltage. The voltage that ring generators use is AC voltage, which means even if the circuit is broken, the phone is on hook, the telco can send a voltage down the line that will make that phone ring. And if you've ever been working on your phone wire while that happens, you know that voltage. It hurts if you're holding that phone wire because it will zap you even if the circuit is broken. So they have a ring generator that makes your phone ring. They provide dial tone. Now, when you pick up that phone off hook, and I guess we could zoom into this phone even to get to a more detailed level. That phone, inside of it, when that phone is on hook, it's pressing down those dip switches on the phone. And when those dip switches are pressed, if we zoom inside of that phone, you kind of have a circuit like this that is broken. And when you pick up that handset and you lift it off hook, those circuits connect. And that is what allows the DC voltage from the loop to flow through your phone. And the CO now knows to provide dial tone, is because, and this is an important statistic here, literally negative 48 volts of DC current begins flowing through the phone as soon as you lift it off hook. Now, I say it's important because when we look at our IP phones and inline power switches and all this whiz-bang wow technology, we'll see that our IP phones run on that same current as our analog phones do. The final thing that CO does is record the digits as we push them. Now, those digits can be dialed in many different ways, but the CO records them and then routes them using the routing table of the PSTN. So if that's what's inside the CO, well, what's inside a PBX? Well, essentially a scaled down version of a CO. The first thing that you'll notice if you open up a PBX, and by the way, this isn't what all PBXs look like. This is just one of many different shapes and sizes that they come in. This is a fairly large one. Inside of this PBX, the first piece that's inside of the backplane of that is the control complex. And essentially, this acts as the brain of the PBX. So inside of here, you'll have all the route functions, the call processing, the dial tone generator, the yada, 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 everything that we talked about in the CO. You have cards, and these are your card slots here, that act as line cards. And these line cards will usually have a connector, depending on the size, but they'll have a little connector on there, or sometimes the card will have two connectors, and it will run off and run down to a connector right here to a patch panel. And this is, a punch down block that will go to our individual wall jacks where these digital phones connect. Now, these cards are usually called, or I shouldn't say the cards are called line cards. The connectors on these cards are usually called amphenol connectors. And I'm not going to even attempt to spell it on the screen. It's something like AMPHONAL, and that's completely wrong, but it starts with an A. And these amphenol connectors will run over here to a punch down blocks. So you have a major kind of connector right here, and it will run and you'll punch down that. It's like a splitter that goes to 24 or 48 phones, depending on the type of Amphenol connector you have. So the line cards will connect off to the end devices, which are typically, in a PBX, digital phones. Now, one thing to note, these digital phones will be, as I mentioned in the very first opening section of this series, they'll be proprietary. So if this is a Nortel or Lucent box right here, you have to purchase Nortel or Lucent phones to plug into it. Now, in the backplane of this switch will be a switchboard, and that is responsible for making all those connections between the devices. When one of these phones calls the other, or one of these phones dial an outside line and connect off to the central office, it's the switch backplane responsible for making those paths and linking them together after it's received direction from the control complex. Now, of course, these devices will have one or more power supplies and fans to make it run. And this is getting into the good side of the PBX. The power supply will typically be redundant and connected to a battery backup. And the good part of these PBXs is they're all-in-one devices. I mean, they have your phone system, the all-in-one package, in the single box. And that makes it really easy to back these things up. You just back up the power to them to a battery, back up your trunk cards to the CO, and that's the next thing I'll talk about, and you're done. I mean, your backup strategy is complete. That's what gives these devices typically 99.999% uptime. They call it the 5 nines, which means you have somewhere around 5 minutes of downtime per year, which is, I mean, compared to the data world, that's insane. I mean, it's very hard to reach that in the data world. But as we get into it, I'll show you ways that we can approach it. Finally, the trunk cards are cards that will connect off to the central office. And these are the cards inside of this PBX that will have your T1 ports, or your analog trunk lines, or your fractional T1 ports to give you the outside connectivity. Now, these trunk cards, let's say we have a T1 line that's 24 channels. Each one of those channels consume 64 kilobits per second of bandwidth. Now, that's a familiar term to us IP telephony folks, because that's, in the data world, a DS0. And we categorize our T1 lines and multiplex them together to allow us to get that 1.5, my dyslexia sets in, 1.544 megabits per second of data bandwidth. But in the voice world, we splice that up into 64 kilobit per second chunks. Now, each one of our voice calls out to the central office eats up one of those DS0s. That plays an important role when we start looking at compressing our voice in the data world. One of the things that you've heard me mention as we've been going through this is key system. I'll kind of use it interchangeably with PBX, like a PBX or key system. And in modern times, it's starting to get really tough to tell the difference between these two, because the people who make the key systems are really ramping them up to have so many features. They essentially are a PBX. But when these first came out, key systems were essentially a scaled down version of a PBX. Now, a PBX, its attributes is it typically connects to digital phones, and that's what we've seen so far. It acts like a CO switch, a little mini-me version of a CO switch. It's scaled down to work inside of a company and allow local connectivity between those phones without paying for a CO trunk in order to make those calls. Now, these are usually used in larger companies that have 50 or more users. So we have a larger base of users that are making these calls and a larger base of features that the PBX supports. And usually you'll dial 9 or some outside access code for an outside line and get that second dial tone effect. So if I call internally, I pick up the phone, hear a dial tone, dial, a 4-digit extension, and we're there. If I hit a 9 or some other outside access code, we'll get a second dial tone, and that means we've utilized successfully one of those outside trunks. A key system, on the other hand, is really a smaller version of that PBX. It can use sometimes analog and sometimes digital phones, and sometimes both. So you can have, your Walmart brand phone sitting on somebody's desk that's using a key system. Usually, instead of each person having their own extension, you'll have a shared line. For instance, my wife used to work at a bank. It was a smaller office that had maybe about 10 employees there that handled the typical transactions. And when I went to visit her, she had a phone on her desk that had 4 lines. And those were the same 4 lines that everybody had in that company. You could hit line one, and that was, the line one that everybody used. And when she used that line one, nobody else could use it. And to tie in with that, you usually would press that button for the outside line. For instance, you would have that office that had those 10 people inside of it, and we might buy, if they had 4 lines, we might buy 4 analog trunks to the PSTN. So when they hit line one, they were really using a line to the PSTN, but they could call internally as well without actually going outside the company. So there was really no second dial tone for them. They could dial an internal extension or an outside line, and that would be the same effect. So it would be typically a shared line kind of environment. And they are used in smaller companies with typically less than 50 users. And I usually say around 10 to 20 users if you have that kind of system of shared line appearances. And as I mentioned, these have really started to change in recent years. You see key systems that really bleed over and start stealing a lot of these features from the PBX to where the line is really blurred between these two. Key systems and PBXs are really starting to be one and the same. It's just the main thing that you'll see is when I buy a key system, they say, oh, this scales up to, say, 50 users, where a PBX can scale up to thousands of users. So that's really the major difference, is how large can they scale. Now, speaking of voice over IP, I love how I do that. Not that I was talking about it at all, but speaking of it, key systems are really starting to support voice over IP as well. You're starting to see the companies that would develop key systems for digital phones and so on add boards to these key systems that allow them to be voice over IP compliant. Not that they're true voice over IP systems because they still use analog and digital phones, but they can use voice over IP communication for a small business to start harnessing a few of those advantages that voice over IP can give you. With that foundation of knowledge laid, I'd love to walk you through a typical phone call process. And I'm talking just a normal phone call. You pick up your home phone and call somebody else across the PSTN. It's actually a really interesting process once you get to know it. The first thing that we see here is that I have 2 phones plugged into a CO switch. Now remember, these are connected on a local loop. I have just a straight line here, but this is really a loop of houses and different phones all around that local neighborhood. And I show them here plugged into the same CO switch, but this could very well be a phone over in Oregon, and this could be a phone sitting in Michigan. It really makes no difference. The magic of the cloud will happen in between and route the call from point A to point B. So I pick up this phone over here, and let's go ahead and label this Oregon. So I pick that handset off the receiver, and I hear dial tone. But what happened to get that dial tone is that a circuit, this CO, first off, is always sending that voltage, the negative 48 volts of voltage, all the way through that local loop. And as soon as I lift that handset from the cradle, the voltage begins to flow through my phone. The circuit is now connected. It's considered off hook. So I pick that up and start dialing on. Look at that keypad. It's awesome. It's a pulse dialing or a rotary phone. So I can drag that phone digit manipulator widget around in a circle, and it will start dialing in that pulse system. The way it does that is it breaks and connects the circuit. For instance, if I go all the way to the 0 right here and let it go all the way back over, it's opening and closing that digit. It's essentially, you could accomplish the same dialing if you have enough dexterity just by tapping the receiver off and on hook on that phone. Now, just about all COs still support pulse dialing, and I was recently given a disturbing statistic that 4 million people still have in the United States these pulse dialing phones. And it's actually, I love these phones. They remind me of a time where everybody wasn't always in a rush because it takes, a lot of time to dial a number. So the digits are sent over to the CO. The CO interprets those and sends those over and says, okay, I'm routing the call eventually over here to the phone in Michigan. Now this phone has the circuit broken. the receiver is on the hook. So in order to make that phone ring, it has to send ringing voltage, which it does using AC current, because the DC circuit is broken. There's no voltage sent. And that's why if you have those wires and you're touching them when it sends the ringing current, you'll get a zap, because it's going to be kind of a different type of voltage that makes that phone ring. So you have it going ring, 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 ring. Somebody answers the phone, links the DC current, so now the voltage is flowing through that phone, and the audio path is connected. The people can begin talking, and their voice will travel through the CO switch as analog waves, and who knows what happens in here. They may be converted to digital and back to analog, but we have people talking. Now, if Michigan were to originate the call, you see the type of phone that they have over here in Michigan. This is a DTMF phone. It stands for dual tone multi-frequency. We often call this tone dialing, or the dialing where you push buttons and hear beeps. And if you were to really get into DTMF, there's a whole standard defined that when you press the buttons on the phone, if we had, forgive my drawing of, looks like tic-tac-toe, but we have this phone, and you have your keypad up here. We have, 1, 2, 3, 4, all the way across. There's frequencies that are assigned, a certain frequency going down and a certain frequency going across. And when you press 1, you're actually combining the top frequency with this across frequency, or I should say up-down frequencies with left-right, and you're having this harmonic being created that's sent to this switch. And that's how it can tell the difference between dialing a 1, a 4, or a 7 down here, is you're using different frequencies in the kind of row format versus up and down. Now these frequencies are all so close together, it's very difficult to hear them. These frequencies, when you start doing them, are distinctly different. And that's why, you've done it at some point. We can dial Mary Had a Little Lamb using these different frequencies going across, but there are differences of going down. And by combining those two tones, the switch is able to distinguish what kind of digit that we're using. There's actually all kinds of frequencies in this DTMF standard for this to relay over a busy signal or a ringing signal, or all kinds of different frequencies defined by this standard that we're able to hear. But once they get to the switch, the processing is the same. The only difference is pulse dialing versus the DTMF dialing that we can use. So that is how a connection happens between two analog phones connected to the PSTN. Now, in a business that's running a PBX system, you typically won't bring in a whole bundle of analog lines just because of the sheer amount of wire that you'd have to have, because each analog line only handles one call. So with a PBX system or key system, you may upgrade to a digital line. And that includes all of those types of lines that are things like T1 lines or E1 lines or fractional T1s or E1s. Or you might end up with a ISDN BRI connection or even a PRI connection. Now I know you might look and go, well, wait a sec. With digital lines, you have T1 and you have PRI. Aren't those the same? Well, kind of, in the sense that they're both digital lines and they both have about the same amount of bandwidth, but T1 uses a signaling known as CAS. And that's why a lot of times you'll hear people say T1 CAS to designate what kind of digital line they're talking about. PRI uses CCS. Now, the thing that dictates what kind of digital line you'll use is typically the CO service provider or the type of connection you're getting at your location, and the PBX vendor. They may only have CAS interfaces for the PBX, or they may only make CCS. Now the difference is this. With T1 CAS, a lot of people call it RBS. That stands for robbed bit signaling. See, when we use a digital line, use a type of multiplexing known as TDM. And forgive me, I'm tying together a lot of acronyms and a lot of concepts in one slide here. What we have is in a TDM, or time domain multiplexing, each voice signal gets its own time slot. Meaning, this T1 line that I have here is really a bundle of 24 individual DS zeros or channels that we can use. And the way it splices those into a single line, I mean, we only have one physical line plugged in, is it splits them up into little time chunks. So as you have, let's say we have 24 calls going out on that PSTN all at one time, you'll literally divide it up into time slices on that line. So each time slice will be a chunk of audio. So we have, Mary up here talking to Mary's, father over here connected to the PSTN, and she is in time slot 1. Now, every single time it runs through, I mean, these time slots are going like 1, 2, 3, all the way up to 24. Start over. 1, 2, 3. It goes through this really quick time slice scenario. So maybe, Mary says, "Hi, Dad, how are you?" And if we could divide it up like this, I could say, "Hi" gets put into this first chunk right here. After this 24, you'll have a 1 starting over. Dad gets placed into that. And this is moving so fast, each one of those time slots are spliced together. And by time Mary's dad hears it out here, he hears, "Hi, Dad, how are you?" through all these time slices being combined back together at the central office. Mary, maybe, Fred over here, let's use a different name. Let's have Jeremy over here is talking to his wife out on the PSTN, Susan, and he's saying, "Hi, Susan, how are you?" He is assigned time slot 2, and we're putting, hi in there and so on. Now, every single one of these time slots are assigned a specific time. That's why they call it time domain multiplexing. And even if there is no conversation, let's say Mary and myself are the only ones talking through it right now, even if there is no conversation happening, still time slot 3, 4, 5, all the way up to 24 still are assigned their same time chunk. Even if they're blank, they end up at the central office. They're not in use. They're assigned a specific interval on that time or on that line that they use every single time they communicate, whether it's blank or whether there's actually audio in there. Now, these T1s that are using CAS and Rob bit signaling mean that inside of that time block, each time block has how much bandwidth? Remember? 64 kilobits per second. Well, technically speaking, all 64 kilobits per second is not used by the voice. RBS, robbed bit signaling, means that we steal some bandwidth out of there, maybe, and I don't know the exact ratio, but maybe all but 1 bit is used, down here. That 1 bit will be assigned to the robbed bit, and that makes up all the signaling for the line, the stuff that passes the caller ID information, the stuff that keeps all your voice in sync and puts, one packet before the other. All of that is put into the robbed bit signaling. And they call it robbed bit because you're stealing bits from each one of these channels to essentially, by combining all of them together, create all the signaling for the line. Now, that does give you some limitations. For example, if you're sending modem signaling across there, it limits how much bandwidth you can consume. You know that if you have a dial-up modem, you can never get 64 kilobits per second. It's always somewhere around, 52 or 48 kilobits per second, maybe 54 on a good day that you're able to get, which is actually a combination of the line quality and the bits that you're stealing. With PRI, you get 23, or common channel signaling, you get 23 audio channels. So you don't get as many audio channels, you lose one, but one of those channels will be dedicated just to signaling. Now, depending on the type of PBX you have, it may require that you have PRI lines so that it can pass that caller ID information on there, that it can pass all its synchronization bits. Everything is spliced separate from the audio channels with PRI. So between the PBX vendor and the central office, they really dictate what kind of technology you're going to use, the PRI or the T1/E1 raw bit signaling, to get that over to them. Now, that's known as time domain multiplexing, splicing each audio signal into its own time chunk. The other type of multiplexing that has been developed fairly recently in telco terms is FDM, which stands for frequency division multiplexing. Now, this isn't usually used on PBX systems. Just about all PBX systems and key systems use TDM, which is why that's the term I use to relate to all the legacy, or I should say traditional, telephone equipment is all kind of TDM based. But frequency division multiplexing is used usually on your analog connections from the central office to a home. Now, that's not my home, that's a dream home. Obviously, it's not in Arizona because there's this green stuff. Some people call it grass. We don't have that here. In FDM, you have your analog connection, and this is your local loop from the central office going to your house. And have you ever wondered, how you can get over your standard phone line, your internet service, and your cable TV all through one pipe? Well, they do that through terms of frequency. The phone and all your voice communication only takes up a small frequency on your line. And if you want to pull up FDM on Google or something like that, you can actually find out the frequency ranges each one of these uses. But with frequency division multiplexing, they have all of the phone communication down at a lower frequency. If you subscribe to DSL for your high-speed internet connection, they allocate another frequency range above that for your DSL links. And that's, they send all your high-speed internet over that frequency, and that is what the frequency your DSL modem uses to communicate. Now, you might have also noticed, if you've had or have DSL connection, you may have noticed that every single phone in the house has to have a little adapter plugged into it. Or now, to save on adapters and save on tech support calls, a lot of the telephone companies have started putting that adapter out at the box on the outside of your house that splits the signal and filters out the internet, because the phones, the phones that you have aren't really set to only use this frequency that you have right here. They're set to use, the whole range. So a lot of times when you sign up for DSL, you'll start hearing this hiss on the line or this kind of scratching in the background. And so they'll put filters on the line that only let it listen to the frequencies that it's meant to. Cable TV that they're sending across your phone lines now is just another frequency that they have right at the top. And that's a range in itself that your cable TV box will be able to tune into. Now again, this is fairly new, and it allows you to have a single line that uses all those frequencies, and there is more frequency ranges that they can expand into as newer services come out. That allows a single analog line to have multiple signals sent across it without them interfering with one another. Well, I hope you've enjoyed the walk down traditional telephony lane, as we've taken a look at all the parts of traditional telephony and really defined what they do. We saw connections to the central office. We even explored the infamous central office and what it does, looking inside of the CO switch and how it routes some of the connections that we're going to form. We also looked at the PBX versus the key system, the PBX being the larger system for companies over 50 users, key system being under 50 users, allowing you to pretty much manage your own phone system within the office. The key parts that we really focused in on what the protocols are, or what signaling standards there are in the time domain multiplexing world. The reason I say that's so key is because the rest of this course is going to be focused in on how to interface with this traditional world, and what kind of interfaces we have that will allow us to speak the language of the traditional world. Finally, we looked at the two multiplexing standards that are out there today for voice. The one primarily used in our digital market, which is TDM, where each voice slice or each voice channel has its own time slot that's always there, no matter if there's voice in it or not. And that's how it separates each of those channels when it arrives at the CO. We also saw FDM, the frequency division multiplexing, where we use frequencies to separate the different signals across analog lines. I hope this has been informative for you, and I'd like to thank you for viewing.